This section 2 on sampling theory is an integral part of the video course Signals and Systems. So you can have a look in the relevant video in this course of Signals and Systems for the details. You will see that there are some new additional slides at the end of the section. I will give you here a quick overview of what is important for this course on digital control, but it goes without saying that sampling theory is of course a very important aspect of digital control. You remember that sampling, or at least ideal sampling, can be modeled using Dirac-Combe sampling. So what you need is here the Dirac-Combe, which is really a train of impulses, of Dirac impulses that are spaced by Ts. So if you multiply this Dirac-Combe with the function that you're sampling, you obtain the sampled function Fs, and if you use the Dirac sifting property, this is what you obtain, and this is how it looks like visually. Okay, so you can see here that the impulse train has been kind of modulated by the function f of t at the sampling instance. So really what is important is, if you know f of t that you're sampling and you know its Fourier transform f of omega, right? The question is, can we obtain also the Fourier transform of this sampled signal, and we'll call it Fs of omega. So the relation between these two will result in the sampling theorem. Well, to obtain the Fourier transform of this sampled signal, you have to remember that the Dirac-Combe is of course periodic of period t of s, the sampling period, and since it is periodic, you can obtain its Fourier series. Okay, so you can write it as a linear combinations of the Fourier functions, where k ranges from -infinity to infinity. So you can really see this as a sum of cosines and sines at, well, harmonics of the sampling frequency. So without going into the details, it is possible to obtain this formula over here, and what you see is here that the Fourier coefficients are all equal to 1 over Ts, and this is what we're going to use to obtain the Fourier transform of the sampled signal. So we have shown that the Dirac-Combe as a Fourier series that is given over here. The sampled signal is obtained as follows, and we know also that the Fourier transform of f of t is given by f of omega, right? So to obtain the Fourier transform of the sampled signal, well, we can use the linearity properties. Okay, so we plug in, of course, this one in here, and we use the linearity properties of the Fourier transform, right? And this is what is obtained. You know the Fourier transform of f of t, it's f of omega. So by the frequency shifting property, you also know the Fourier transform of this signal multiplied by this exponential. Okay, so in frequency you'll have a shift of k omega s. So what you see here is that the Fourier transform of the sampled signal is obtained from the Fourier transform of the original signal. Well, really it is a superposition of shifted analog spectra of this type multiplied by 1 over Ts, and knowing this, we'll be able to obtain the sampling theorem. We can now use this to obtain the so-called Nyquist condition. So we can see here that we're considering a signal that has a low pass spectrum of finite support. So what you see here is the amplitude Fourier spectrum, and indeed you can see that there is a frequency content in the low frequencies, but at above the frequency omega max there is no frequency content. You know that in reality there will still be some frequency content over here. So we can now have a look at the Fourier amplitude spectrum of the sampled signal, and indeed what you see here is that you have a sum of shifted versions of the original spectrum, okay, or motive, shifted by k omega s, but they are also kind of multiplied by this factor 1 over ds. Okay, so at reconstruction, what we'll do is select everything in between minus the Nyquist frequency. Okay, so this is minus omega n and plus the Nyquist frequency. So you can see that as long as omega s is chosen large enough, right, these two motives in blue will not overlap. If omega s is chosen too small, these two motives will be overlapping, and well, at reconstruction you'll have frequency folding problems. So the Nyquist condition comes from the fact that this point over here, so this is omega s minus omega max, must be larger or equal than omega max, right? So omega s is larger or equal to 2 times omega max. And well, this Nyquist condition is often written in terms of the Nyquist frequency, which is a half of the sampling frequency, and the Nyquist frequency should be larger than omega max. Okay, so it should be larger than the maximum frequency that is contained in your signal. So this is the summary on the Nyquist condition. Suppose that f of t is such that the maximum frequency present in the signal is omega max, then it is possible to choose omega s in such a way that you do not have frequency folding, you do not have overlapping of the motives, and you have to choose omega s in order to obey the Nyquist condition. Here it is, with omega n, the Nyquist frequency. Again, I will not review all the examples. Remember that you can have a look at the video course Signals and Systems if you have forgotten, but clearly you have to be able to apply the sampling theory, for example, to a sinusoidal type signal. So if there is aliasing, for instance, you have to be able to determine under which frequency the aliased signal will present itself. In this course, we will not go into the details of the sample and hold mechanism, quantization, and digital coding. Well, of course, you can have a look in the video course Signals and Systems. What you see here on the screen is the whole analog to digital conversion chain, and of course you start with an analog signal at the input, and remember that when you sample you should meet the Nyquist condition. Okay, so if there is a danger of not meeting it, you should filter your analog signal using a low pass, so-called anti-aliasing filter, and the idea of course is to remove all frequencies that are above the Nyquist frequency. So this is going to be an analog filter with sufficient roll-off. So you assume here that the slope is high enough so that you can effectively remove all frequency components above the Nyquist frequency. So at the output you obtain another analog signal that you can now sample without danger of frequency folding. The next operation is the sample and hold operation. So the idea is that you sample a signal so that you obtain a sample of the signal at the precise sampling instant, and then this sample is held so that you can do quantization and coding. Very often this sample and hold operation is assumed to be ideal, but remember that it is not, because the sampling period is not really constant. There will be very small variations, and also you cannot assume that the sampling is ideal in the sense that it is instantaneous. Well, the value of the sample will be the average around a small period around the sampling instance. Well, after the sample and hold process, you have a sequence of real numbers of infinite resolution. So what you'll do is quantization. So you'll use a quantization grid to make sure that, well, these sequence of numbers are such that they have a finite resolution. So at the output of the quantization step, you obtain a sequence of real numbers that are ready for digital coding. This sequence of real numbers with finite resolution are now digitally coded over a number of bits. The number of bits that you have also kind of defines the number of quantization levels that you will have in your quantizer. At the end of the digital coding, you obtain a sequence of integer numbers. So if you assume an infinite resolution in the quantization step and you assume ideal impulse sampling, and you stop kind of here, so that you neglect the coding, well, you can view the analog to digital conversion as a process that takes an analog signal, and the analog to digital conversion will convert it in a sequence of real numbers that are the value of the function at the sampling instance k times ts. Let us take an example from practice. Suppose that we are given a temperature transmitter with the following characteristics. The range is from 0 to 200 degrees Fahrenheit, so in degrees from minus 18 degrees to 93 degrees Celsius, and the output that corresponds is varying linearly with the temperature to an output between 4 to 20 milliamps. We will assume here that we're using an analog input module that measures the current and the 4 to 20 milliamps with a resolution of 15 bits. This means that these 4 to 20 milliamps that are measured are the image of the temperature that goes or that varies in the range from minus 18 to 93 degrees Celsius. After quantization and coding, 4 milliamps will correspond to a binary number where all the bits are at 0. So this will correspond to the integer number 0, and 20 milliamps will correspond to the binary number where all the bits are at 1. And so this will correspond to an integer number which is 2 to the power 15 minus 1. So we are now in a position to compute the resolution or quantum or least significant bit. And what we do is take the measurement range, 93 minus 18, so 93 plus 18, divided by the number of quantization steps, 2 to the power 15 minus 1, and this leads to a resolution of 0.0034 degrees Celsius per bit. And remember also that the quantization error varies between plus minus the least significant bit divided by 2. We will now consider the digital to analog conversion, and we have seen last year that you can reconstruct the signal using this ideal reconstruction filter shown here in red. This is how you do things in the frequency domain, but if you look at the corresponding ideal low-pass filter in the time domain, then you will see that it has a non-causal impulse response with an infinite support. This means that this filter is not realizable in practice. For this reason, we have considered more pragmatic ways to reconstruct an analog signal, and these involve hold mechanisms, and more in particular the zero order hold, which is often used in practice. Refer to the video course Signals and Systems for more details. The zero order hold, or ZOH reconstruction process, can be represented by its impulse response. Of course, this is the case for any process that is linear time invariant. So the question is, how do we obtain the impulse response? Well, the answer is simple. We have to put an impulse at the input of the process, and here the process is this zero order hold reconstruction. If we put an impulse at the input, what this process will do is maintain it, hold it for a period of time Ts, and after Ts, well, the signal will fall back to zero. So in blue here you have the impulse response of the zero order hold reconstruction process. So ideal sampling followed by ZOH reconstruction can be modeled as follows. Here you see the ideal sampling. The sampled signal is obtained simply by multiplying the original signal with a Dirac comb, okay, and from the sampled signal you can obtain the reconstructed signal by simply going through a zero order hold reconstruction process. This process is characterized by its impulse response, and the impulse response is given over here. You notice that this time the impulse response is causal. So let us look at this zero order hold reconstruction more in details. Remember that the reconstructed output is the convolution of the sampled signal with the impulse response of the ZOH process, and remember that this impulse response looks like this. So it will maintain the impulse for Ts, and so this is how it looks like, right? So we would like to see, well, what is the Fourier transform of this signal over here. Okay, so the Fourier transform of the reconstructed output will be Fr of omega. And since you take the convolution in the time domain, you know that this is going to be a product in the frequency domain. So what we can do is take Fs of omega. Remember that Fs of omega is a sum of scaled versions of the original Fourier transform that are shifted by k omega s, and omega s is the sampling frequency. And then you have to multiply by the Fourier transform of this impulse response signal. Okay, so what we need over here is to compute the Fourier transform. You can do this using the definition. This is what is done over here, but you can also remember that this signal here, which is the impulse response here, it has finite support. Okay, I should complete it and write it like this. So if it has finite support, you can use this trick of computing the Laplace transform of this one, and then replace S by j omega. Okay, and you can easily see that the Laplace transform of this signal over here will be two steps. Okay, so maybe let's first construct the impulse response itself. It will be u of t minus u of t, t minus ts. And if you take the Laplace transform, this will be, well, 1 over s. That's because of the steps. You'll have a 1, that's the Laplace transform of this one, and you'll use the time shifting property, so you'll have minus the exponential of minus ts s. So if you replace s by j omega, well, you have an expression of the Fourier transform. Okay, then of course you can go through the calculations and see that it is indeed a cardinal sign. So we had seen that using ideal reconstruction, at least assuming that the Nyquist condition is verified, we can reconstruct the Fourier transform of the original signal. But we remember that this ideal reconstruction in practice is not realizable. This is why we looked at a pragmatic way to reconstruct the signal, which is the ZOH reconstruction. And again, if we assume that this Nyquist condition is respected, this is what you obtain. If you multiply this one by TS, right, what you obtain over here is the Fourier transform of the impulse response of the ZOH reconstruction filter. And if you multiply this one by 1 over TS, what you have over here is the Fourier transform of the sample signal, and of course these two will cancel out. And what you can already see is that, well, the spectrum of this reconstructed filter is distorted by the spectrum of the impulse response of this ZOH reconstruction filter, and that the repetitions of the spectrum, you can see it over here, are still present, although they will be attenuated. What we'll do now is visualize this using the amplitude spectrum. So here we reconstruct the spectrum of the ZOH reconstructed signal step by step, and we start with the spectrum of the original signal that is sampled, and here it's the amplitude spectrum, as you can see. And we remember that we have taken a signal that has low pass spectrum with finite support. So what we have done is, for instance, used a low pass filter to remove all components above omega max. After ideal impulse sampling of this original signal, we obtain the sampled signal fs of t, and if you take its spectrum, well, you can see here in blue that the amplitude spectrum becomes periodic of period omega s. So the blue amplitude spectrum can be obtained from the spectrum of the original signal, and this is the central motive in green, by simply scaling this central motive and then taking shifted versions at frequencies k omega s, and though this is how you obtain this periodic spectrum at period omega s. So what we show next is the amplitude spectrum that is associated with the ZOH reconstruction. Okay, so remember that we have taken the Fourier transform of the impulse response associated with this reconstruction, and if you compute its amplitude spectrum, this is what you obtain here in cyan, and you observe that at zero frequency you have Ts over here, and you can also clearly see that at frequencies omega is equal to k omega s, well, this sign here will produce zeros. This is what you see over here, and further on the line as well. So what we'll do now is compare first this amplitude spectrum of this cardinal sign with the ideal reconstruction filter, and what we'll do next is compute the spectrum of the reconstructed signal, and this will be obtained by taking this one over here, okay, and multiplying it by this one over here, and we'll be able to show this visually. So here's the ideal reconstruction filter. It's a rectangular window that selects all frequencies in between minus the Nyquist frequency and the Nyquist frequency, and in this frequency band it multiplies everything by Ts, and you can see that this ideal reconstruction filter will be able to kind of reobtain the original spectrum from the central motive in the ideal sampling spectrum. This looks very nice in theory, in the frequency domain, but in practice this ideal reconstruction filter is not realizable, because in the time domain it will involve, well, a convolution with a non-causal cardinal sign. You can see here in this amplitude spectrum that the ZOH reconstruction is only a very crude approximation of the ideal reconstruction filter, but at least this ZOH reconstruction can be implemented very easily in the time domain. And finally we obtain the amplitude spectrum of the reconstructed signal using ZOH reconstruction, and this is simply done by taking this spectrum over here and multiplying it by the spectrum of the cardinal sign. There are two things that we can observe. We still see the presence of the repetitions, although if you go further in frequencies these repetitions will be attenuated more and more. And what you see also that in the frequency band of interest, minus Nyquist frequency to Nyquist frequency, that we have kind of distorted the original spectrum. It is not reconstructed perfectly even in this frequency band of interest. We have shown that the recovered signal is distorted. The repetitions in the spectrum are still present, although attenuated. So in practice what is done is that the sampling frequency omega s obeys the Nyquist conditions, but will choose omega s much larger than 2 times omega max, or equivalently will choose the Nyquist frequency much larger than omega max, and this is to attenuate the distortion effects. This is known as oversampling. So by doing oversampling, omega s is chosen much larger than 2 omega max. You have two advantages. So omega s will move to the right, so the repetitions will be at higher frequencies, but of course this cardinal sign will be kind of stretched, okay, and you will see that inside the interval minus omega max the effect of the distortion will become smaller and smaller as the cardinal sign here in this interval minus omega max will be lifted. Okay, so the effect of distortion in the frequency band of interest becomes smaller. Well, the ZOH reconstruction procedure is often followed by a low-pass, so-called reconstruction filter. This is to remove all components above the Nyquist frequency, and in this way you'll be able to remove the influences of the repetitions of the spectrum. Sometimes an additional filter is used to kind of invert the distortion effects inside the frequency band of interest. What you see over here is the complete picture when you do digital to analog conversion. So obviously the first thing that is done is digital decoding. So you take the original sequence of integer numbers, and after digital decoding you obtain a sequence of real numbers. Well, this set of real numbers at the sampling instance is sent to the analog hold process. In our course it's the zero order hold process, although you know that it's also possible to find other analog hold systems such as the first order hold, and what comes out is an analog signal in the form of a staircase. We have seen in the spectrum of the reconstructed signal that you could still see the influence of the repetitions in the spectrum. So very often a reconstruction filter is used. It's a low pass filter and it will remove everything that is above the Nyquist frequency. Here again we'll take a filter that has a sufficient roll-off, so the slope is high enough over here. What is done sometimes also is to use a filter that will kind of invert the distortions in the frequencies of interest, from minus the Nyquist frequency to plus the Nyquist frequency. After this filtering operation you recover an analog output signal. So if we neglect the decoding effect, so we start from here, you can see the digital to analog conversion, and we'll kind of visualize it as taking a sequence of real numbers, and this digital to analog conversion will transform it into an analog output signal in the form of a staircase that is constructed on this sequence of real numbers. In this slide what we do is analog to digital conversion followed directly by the reverse conversion, digital to analog conversion. So we make a number of assumptions. We assume that the quantization step is ideal, so we kind of use a quantization grid that has an infinite number of levels, and we assume that the sampling is done using an ideal sample and hold. In practice this is not the case. We remember that the sampling instance will not be regular. There will always be small variations in TS, and also we cannot assume the sampling to be instantaneous. But these are the assumptions that we make. If you make these assumptions, the analog to digital conversion followed by digital to analog conversion will transform the input analog signal into an analog signal in the form of a staircase, and you can see the discontinuities at the sampling instance. In this ideal analog to digital conversion followed by digital to analog conversion, the predominant effect will be that of the zero order hold, and remember that the zero order hold can be described by its transfer function, and the transfer function is the Laplace transform of the impulse response of this zero order hold process. The 1 over Ts comes from the analog to digital conversion, and it will cancel out with the Ts that is hidden in the transfer function of the zero order hold mechanism. Well, we have just seen that the combined effect of analog to digital conversion and digital to analog conversion can be described by this transfer function over here. If you remember the Taylor series of the exponential, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on, well, you can kind of rewrite this expression here as follows. Okay, so if you plug this, will stop at the second order term here. If you plug this expression over here, this is what you obtain. The 1 and the minus 1 disappear. You have a TS here and a TS here. This one will cancel out, this one will cancel out. Here we have a TS square, so we have a TS that is left, right? So also you have a cancellation of the 1 over S with this one. Here you have a S square, so this leaves you with S, right? So this overall effect of the analog to digital conversion followed by digital to analog conversion can be approximated as follows. And here again we can use this Taylor series to see that this is approximately a transfer function that models a delay of Ts over 2. So the combined action of analog to digital conversion followed by digital to analog conversion introduces a delay of half the sampling period in the control loop. So if this delay of Ts over 2 has not been taken into account in the control design, it can give rise to problems when Ts increases. Okay, when you choose a really small Ts, and you should always say with respect to what. So if you choose Ts very small compared with the main time constant, will this delay will not have a major impact. But when Ts increases, right, this effect will become larger and larger, and in the end your design, that is the closed loop response with the discretized controller, will no longer meet the original specifications. So what we'll do here is kind of illustrate this in Matlab so that you can see things visually. We'll consider a signal x of t, which is the sine of omega 0 t, and omega 0 is 0.3 radians per second. And then what we'll do is sample this signal with a Ts of 1 second. Okay, so this is this sampling period. Okay, and this gives me the sampled signal. I also want to represent this signal, which is really continuous time, but we have to represent it in Matlab, so we also kind of need to sample it just for representation. So what I'll do is take a sampling period for simulation that is of course much smaller than the actual sampling period, right? And this is going to represent the actual signal x of t, and when we'll look at the curves, it will look almost as if it is really a continuous time signal. So what we'll do is take the original signal x of t, and it will go through this transfer function. And remember that this transfer function is meant to represent the effect of a combined analog to digital conversion directly followed by digital to analog conversion. And this is how you can do this. Well, you have to kind of take an integrator, right? Remember that this is 1 over s minus 1 over s e to the minus ts, right? times 1 over ts. So this one is simply going to model a system that is just an integrator. This is the integrator with the delay. We take the difference and then we multiply by 1 over ts. And what we do is we simulate the system with this signal over here and this difference here, 1 over s, and here 1 over s times e to the minus ts s, of course. So this signal y will be x going through this transfer function, and what we can then do is have a look at the different plots. So you can see here the result of this Matlab code. In blue, the sine function. In purple, the samples. So you can see here that the samples are over here, etc. But since we have used the command stairs, this is how it looks like, right? And the reason we have used the command stairs here is that it kind of shows what would happen if you take the sampled signal and you make it go through a zero order hold. Then you would really have this signal in purple. What you have here in orange, I guess, is the original signal going through this transfer function that mimics the combined ADC and DAC effects. And you can clearly see, and of course here you have of course an initialization problem, but after some time you clearly see that there is here on average a delay of roughly ts over 2.